Okay, so hello, I'm Anita Arora and I'm going to talk about the monopole diameter model on the Cartesian product of plane graphs. This talk is based on a joint work with Professor Arvind Iyer. Let's consider a graph G which is simple and weighted and has an orientation O. Its vertex weight will be given by XV and edge weights will be given by AVV dash. A loop vertex configuration on G is a subgraph which consists of directed loops of even length, some doubled edges and isolated vertices, with the condition that this collection will form a cover for the vertex side of the graph G. The collection of all such loop vertex configuration will be denoted as LG. Let us see what a loop vertex configuration through an example. Consider two matchings, red one and blue one, over the grid graph with unmatched vertices at the same location. When we superimpose them, we will get a structure like this. And this is a loop vertex configuration with the condition that each cycle of length strictly greater than 2 has a direction, either clockwise or anti-clockwise. For example, consider this graph on 4 vertices. Loop vertex configuration corresponding to directed cycle 1, 2, 3, 4 has been shown in figure B, and a loop vertex configuration corresponding to a double edge at 1, 4 and isolated vertices at 2, 3 has been shown in figure C. Now, we haven't used the orientation of the graph till now. Let's use it to define a sign, to associate a sign with each edge. An edge will have a sign +1 if it is oriented from Vi to Vj and -1 otherwise. Now, the loop vertex model is the collection of all loop vertex configuration together with the weight function. That weight of the configuration is the product of the weight of the loops involved in it and product of the vertex isolated vertices weights, where the weight of the loop is defined as taking the product of sign and edge weights of the edges involved in the loop L, and there is a minus sign as well together with the product. So now you can note that this weight of the loop is depending upon the orientation because the sign is defined using the orientation. So it's a orientation dependent model. Now let's say partition function of the loop vertex model is the sum of weight of the configuration, where sum is taken over the all possible set of configuration over the graph G. Professor Arvind Iyer has shown that this partition function comes out to be determinant of a matrix K, which is sum of a diagonal matrix and a skew symmetric matrix. Now let me recall some basic definitions. A plane graph is a graph which can be drawn in a plane without any edge intersection, and such a drawing of a plane graph will be called as a plane graph, and such a drawing of a planar graph will be called as plane graph. It divides the whole plane into some regions, they will be called as faces. There is a special orientation for the plane graphs called the Pfaffian orientation. Pfaffian orientation is said to have clockwise odd property because it is defined as an orientation in which if you move in the clockwise direction along any bounded face, then you will encounter odd number of clockwise edges. So that's why it is called as clockwise odd property. Now what happens if you consider graph to be a planar graph and it has a Pfaffian orientation with it, then the loop vertex model can be expressed in an orientation independent way, and this is what here is enclosed by the loop L and the product of the edge weights that are involved in the loop L. In other words, loop monopole diamond model is an orientation independent interpretation of the loop vertex model for the planar graphs. And it has been shown that the partition function in this case again turns out to be the determinant of a matrix, and hence determinant becomes independent of the orientation. Now, in this work we have extended the monopole diamond model, which was defined for the planar graphs. We have extended it for the Cartesian product of plane graphs. First of all, let's consider a plane graph which is bipartite. The sign of a cycle decomposition for such a graph is defined as the product of -1 to the power number of vertices enclosed by the cycles that are involved in the cycle decomposition plus 1. Now, what happens if you have a bipartite even plane graph? Then, however you choose the cycle decomposition, its sign will remain same. So, this sign will not depend upon how you choose the cycle decomposition. Now we are in a good shape to define the monopole diamond model on the Cartesian product of K plane graphs. So for that, let's consider G1, G2, Gk, which are plain simple graphs. For the timing, let's consider them to be bipartite and they have orientation which is Graphian O1, O2 up till OK. Let P denote their Cartesian product with an orientation defined using the orientation O1, O2, OK. Then the ith projection of any subgraph in P is defined as that subgraph after contracting all the edges but the GI edges. Now our goal is to interpret the weight of the loop such that it will not depend upon the orientation. So for that, let's consider the loop L in the Cartesian product P and take their projections L1, L2 up till Lk. So now L1, L2, L1 delta, L2 delta will not be a cycle, they will be a closed trails. So we can find a cycle decomposition of it. Let Di be a cycle decomposition of the ith projection. Then the sign of the loop can be written as the product -1 to the power Ei into sign of the cycle decomposition. By the lemma that we just discussed, the sign will not depend upon how you choose the cycle decomposition. So this is well defined, and Ei is a quantity which is coming from how you have assigned the orientation over the graph using the orientation O1, O2, OK. Now one can note that this quantity in 2 will not depend on the orientation O1, O2, OK. So it's an orientation independent interpretation, and in this case also the partition function comes out to be determinant of a matrix, which is again sum of a diagonal matrix and an anti-symmetric matrix. I have explained it for the bipartite case, but we have also extended this interpretation for non-bipartite case, in which we have to restrict this collection of cycle decomposition to a particular collection of cycle decomposition. Now let us consider a three-dimensional grid example, which is also a Cartesian product. This is a Cartesian product of P3 with P2 with P3. It has a labeling 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's a snake-like labeling, and it is called as Westerfordon labeling. If we consider the grid graph, the three-dimensional grid graph with even lengths, and the orientation is coming from the labeling, that is lower labeled vertex is directed from an edge is directed from a lower labeled vertex to a higher labeled vertex, and assume that all the vertex weights is x, and A, B, C are the edge weights for the edges pointing in x direction, y direction and z direction respectively. Then the partition function comes out to be this product. And one thing to note about this product is that it's a fourth power of a polynomial, and these cosine terms need not be integers, but after taking the product it will always comes out to be a integer polynomial. Similarly, we have done it for the d-dimensional grid graph. If you take a d-dimensional grid graph with even grid lengths and all the vertex weight be x and ai be the edge weights in the possible directions, then the partition function of this monopole diamond model comes out to be this product formula. Again, you can note that the power comes out to be 2 to the power d minus 1, and again it's an integer polynomial. Again, it's an integer polynomial, which is not evident by just looking at the formula. Now, there are possible scope for this formula. If you consider it for the two-dimensional case, then this term that is inside the power has been interpreted, but for the d-dimensional case, we still look for an interpretation for this formula because it's nice, but we are not able to find it yet. So this is the possible scope of this work. One is we can extend the monopole diamond model for other graphs as well. So we would like to find some other class of graphs for which this orientation independent interpretation will extend. This first reference, you can find everything, all of the proofs that are mentioned in this slides. And the second reference is basically, it has the monopole diamond model, the monopole diamond model for the plane graphs, and the loop vertex model. If you want to study about the starting points, then this paper is an educated, and this is a beautiful paper.